So just our last talk lining up for the end of our APAC summit is Saravana Kumar. He has as the cybersecurity lead for Transport for New South Wales, based in Sydney. He's got 25,000 odd people working to make New South Wales a better place to live, work, and visit. It's an incredible environment to be responsible for, especially when you get into that rail signalling, interlocking vital networks and similar. I think, as I said at the top of the summit, that rail OT environment is an incredibly a challenging one, especially where you might be dealing with kind of like a high consequence, high likelihood event, especially tying in that to safety. Before the Transport for New South Wales, he was working with Deloitte, KPMG and others, masters in cyber law and info security. Fantastic. Again, put your questions in the Zoom Q&A, but without any further ado, we'll hopefully hand over to Kumar. All over to you, mate.
Yeah, thanks for the introduction, Peter. Hello, everyone, and thanks for joining in. And as Peter mentioned, this talk will focus on an experience from the asset owner standpoint in embedding cybersecurity as part of the engineering lifecycle for a transportation system. And a quick disclaimer before I start, the views discussed in this session are mine and does not represent my employers. So before we start a rundown of the agenda, we'll start with some system engineering basics, and we'll look at common challenges we face in securing control systems and reasons why cybersecurity should tap into system engineering. And following that, we'll walk through an approach that we leverage in one of our programs to embed cybersecurity as part of the engineering lifecycle, taking guidance from standards like 62443 across phases. And to wrap up, we'll briefly discuss some guardrails we considered through this process. So system engineering, to break it down, as we all know, a system is a combination of elements, say, to achieve a purpose or a function. And these elements could include people, process, hardware, software, tools, all that is required to perform that function. And system engineering is simply the approach to piece together those different elements and disciplines to achieve the defined outcome. And it really bundles up everything, defining the need for the system, documenting the requirements that has to be met across the system's lifecycle to realize the benefits and assess the adequacy and accuracy of the requirements to produce a design involving stakeholders from various disciplines, and using testing regimes to verify and validate whether the system fulfills the requirements and meets the operational needs of the asset owner. So this is just a graphical representation of the system engineering lifecycle. It's also referred as the V model. And it starts with the understanding of business and operational needs of various stakeholders. So this is where we have our business requirements written up, and we start to conceptualize the impacts on the operations and maintenance practices across people, process, and technology. And following that is a system definition phase where we prepare system requirements across disciplines. And depending on the size of the system, it may be broken down into multiple subsystems. And a subsystem is another system in its own right, but it won't serve any useful function on its own. And this diagram is just a representation of a large-scale industrial deployment where a system is broken down into multiple subsystems. And it is at the system definition phase where we baseline our requirements, and we then move into the design phase now, which may happen both at a system and a subsystem level, where we engage with our service providers, the integrators and suppliers to discuss interfaces, assumptions, perform risk analysis, and really define how the system will be integrated tested and accepted. And towards the end of this phase, the design baseline for the system and subsystem is finalized, which is then used for the product manufacture and install phase. And post that, we perform verification and validation activities at a subsystem level. Now, this includes the FAT and SAT, and then the integration of subsystems happens at phase 6 now to form that wider system. And then we perform verification activities at a system level. And towards the end, there's an operational testing that's performed prior to handover, which is primarily focused on the business roles and processes that will interact with the system through its life. Rail systems, there are a few train control systems out there, and the concepts around train detection and controls vary slightly across the systems. This is just a depiction of a European train control system. So just to simplify and relate this to the Purdue model, the traffic management system is more like a supervisory control. The operators use the system to set the route for a train, which flows down, this information flows down to the interlocking and the radio block center, which could be considered as control and safety put together. The interlocking verifies if the track is clear through its sensors called axle counters. And it also ensures the tracks are positioned correctly through its actuators called points machine. And then it reserves those track sections for the train and informs the radio block center it is safe for the train to proceed now. And then the radio block center sends a movement instruction or a green signal to the train through a GSM network. And the European vital computer or the EVC on the train acts on this, either automatically moves the train or allows the driver to manually operate. And there are several other systems, such as passenger info, CCTV on the train, which could again be spread across the layers of Purdue model. And there's also electrical SCADA and a lot of planning systems that support the train operation. So it's quite a diverse environment, and has significant exposure due to its nature of operations, that is operating in the public corridors. And the cybersecurity challenges are no different from other industrial environments. The systems last for decades, and there's always a chunk of legacy system on the production floor with its own constraints that needs to be worked around. And due to their mission critical functions like signaling and safety, they're always expected to be available, which makes, again, the defender's job tougher to assess and make any sort of modifications to the security posture of the system. And the life cycle also involves a wide range of stakeholders, including operations, maintenance, safety. So cybersecurity matters needs consensus across the board, and it may slow down or delay the initiatives. And also the asset owners, they heavily rely on the suppliers, and in all instances, suppliers hold through life contracts to support the asset owners' operations towards meeting the system's reliability and safety targets. So we need the suppliers' buy-ins for deploying any security controls around their products. And also the consequences of introducing an unplanned or untested change to the environment, including introduction of security controls without planning or thorough testing, could also result in health and safety incidents. So it is crucial to tap into the design process of train control systems earlier on, as we all know, rather than retrofitting. And system engineering sort of provides the perfect means to do it. So the next slides will focus on some of the key activities that we performed across the phases. I'll not be getting into the specifics of the system due to legalities. And yeah, so starting with the business and operational needs. So this was by far the most important phase. As you all know, transportation systems are heavily regulated to reduce safety risks to as low as reasonably practicable. And as Peter alluded to earlier, it is at the center of everything that the industry does. And the safety and cyber connection forms a strong case for cybersecurity requirements. And we had those requirements explicitly stated since the end solution will be validated against it. And we also had a management plan defined that discussed the governance and assurance regime, listing activities that will be carried out across different phases of the engineering management lifecycle, discussing responsibilities of stakeholders and the artifacts and deliverables that are expected from our service providers, including integrators and suppliers. And we also worked closely with the engineering team to understand the operations and maintenance concept of the solution. That's usually on a concept of operation document. It helped in conceptualizing what the system is, what functions are expected, its potential interfaces, and we performed a criticality assessment based on that, now considering the worst case consequences for risk events and rating them, taking into account operational requirements of the business and inputs from safety teams through hazard logs and workshops. And we also considered intel from relevant sources. And this exercise was purely consequence driven, since our internal standards mandate likelihood to be considered certain during the concept stage, more inclined towards being risk averse due to potential health and safety related consequences. And towards the end, we prepared a preliminary zone and conduit model with initial security level targets. And this was more like a baseline, which helped us in avoiding instances where service providers may over or underestimate the cost of security controls. Although it wasn't accurate, but it did help both the parties, the asset owner and the service provider, to estimate their security budget. And the 62443 standards that we leveraged at this stage was 3-2 that provides guidance around risk assessment and partitioning the system into zones and conduits, and 3-3 that describes the system security requirements. And it was the owner's team that held the responsibility of this phase. And in this phase, now we had a system integrator come in now to help us define the system and its requirements across all disciplines, including cyber, both from security, technology, risk, and compliance perspective. Now the compliance requirements included regulations, organizational policies and standards, and adherence to the risk management procedure, so that all service providers utilize the same approach to assess and mitigate risk across phases. And on technology-related requirements, now we wanted to be explicit on the security functions of the system. Now it stemmed from the security level targets that we set, and also a few Rail-specific standards. And since we were on a project that was implementing a system of systems, that is looking at multiple system integrators and suppliers, who were all contracted at different points in time, each treating their chunk as a system. We developed an integrated system level conceptual architecture as a reference, really to depict how security functions delivered across different subsystems will come together at an integrated system level. The rationale was not to centralize or integrate everything. It was purely a risk-driven approach based on the zone and conduit model of now the integrated system. The primary intent was to avoid silos of security controls across the system. And we also defined requirements related to our service providers security program that would help us in defining policies and procedures based on the capabilities specific to the system. As we all know, the one-size-fits-all approach doesn't work. So this was to engage service providers in contributing to the asset owners' cybersecurity management system. And we use terminologies from 1-1 to avoid ambiguities on the requirements, 2-4 to define the security program requirements for our service providers, the terms around which was negotiated during the contract award, and 3-3 for expanding on the security level target related requirements. The challenge was to define the expected security functions without being too specific, because all our service providers were all authorized engineering entities to design and deliver fit for purpose assets. So we just can't enter into the design space of the engineering entity. So we just have to draw a line. And the integrator who defined the security requirements, the system requirements, held the responsibility of this phase. And since we had early contractor involvement arrangement, the suppliers were also consulted on a need basis through this phase. So the preliminary design, this was post-contract award, and it really started with the review of the system definition. That is primarily validating the inputs and clarifying on the assumptions from previous phases. And although we signed a contract setting the baseline requirements for each subsystem, we did have an exercise to engage our service providers to revisit the outcomes of the criticality assessment that we performed during the business and operational needs phase, to have their insights and to also validate the credibility of some consequences we defined earlier. Although we had bits of this discussion prior to the contract award, in this phase, we got to discuss things to a greater depth before kickstarting any design process. And as we all know, it is a common engineering practice to have management plans written up at a subsystem level to ensure subsystems deliver as per the principles and approaches defined at a system level. So the service providers, security management plans were all reviewed for its alignment with what we had stipulated at a system level to verify if it addresses the deliverables and assurance artifacts across phases. And by this stage, we were also across the key components that will form part of the system, including our controllers, our workstations, network devices, embedded devices. So we engaged in defining how these components will interface with any external or centralized cybersecurity function, the ICDs and ISTs, say for monitoring, remote access. And the conceptual architecture that we developed in the previous phase sort of provided a good starting point for this exercise. And in terms of standards, 3-3 and 4-2 were used to discuss and agree on the security functions defined at system and component level. And the system integrator owned the primary responsibility here, supported by our product suppliers. So yeah, the detailed design phase, it started with a detailed risk assessment. We did face some challenges in achieving consensus on the risk assessment procedure, despite having compliance requirements, since our service providers, like I was mentioning earlier, were all authorized engineering entities, and they had their approaches to assess risks and derive security level targets for their products. And the project's intention was also not to customize and just configure the proven COTS product. So we really had to find a common ground to tweak their approach and metrics not to align with what we had now as an organization. And the operations and maintenance scenarios now were also defined based on the security functions of the system. It was primarily around modeling how system functions will interact with the people and process components, which helped us sort out the dependencies on our just the asset owners security organization, that is the security roles, and competencies, process and procedures. And we wanted to have those gaps identified, and addressed before the system undergoes operational testing, so that we could verify the effectiveness of those controls as well. And the service provider's security program was also reviewed based on our CSMS needs, including security practices and documentation, primarily focusing on how do we actively defend the system through its life, starting with the baseline information on each asset for our inventory purposes, suppliers, process around communicating on product weaknesses, how are we going to do patch management, security hardening, including audit log configurations, and even log retention on devices, especially the high-risk ones related to the operations, and documentation on extracting information from those devices if required. And the attempt was really to build something close to what Dragos calls a collection management framework, at least from the log management perspective. And the test plans were also agreed so that the testing arrangements could be factored in as part of the design. And it involved defining test cases and methods and the environment that will be used to verify and validate each control, say using penetration tests, inspections, or walkthroughs. And in terms of standards, 2-3, the technical report on patch management was used as a guidance for finalizing the patching plans and policies. And our service providers were contractually obligated to leverage 2-4 to deliver on the asset owner's CSMS requirements, and 3-3 and 4-2 for design discussions on security controls at system and component level. And for test plans, we refer to the testing specifications for system and component and embedded device, security certifications from ISA Secure program. And the accountabilities and responsibilities now remain the same as the previous phase. So phases 4 and 5, we had our suppliers install and configure their systems as per the approved baseline for the design. And we performed a test readiness review to verify the hardware and software revisions to avoid investing efforts on a setup that is either not appropriate or not mature enough for testing. And the SAT artifacts were reviewed for their alignment with the agreed test plans and procedures around tooling, type of tests, and the results. And any deviations from the approved design now to enable testing were also noted and resolved after the testing. Now this included changes to the standard configuration, like say turning on debugging, creating a test user account. And towards the end of this phase, now we also verified artifacts related to patching as per our agreed patch management plans. And yes, we were not able to fix all the issues. So the obvious fallback was to consider compensating controls and tweak some rail operational procedures as controls, again in consultation with the ops and safety teams. And contractually, the suppliers were obligated to consider 4-1, the standard that talks to requirements for secure product development lifecycle, although we were buying COTS. 4-2 and testing specification from ISA Secure were used as references. And the suppliers held the responsibility of the manufacture and install phase, while the subsystem integrators were responsible for subsystem testing. And at the system integration phase, the verification and validation was performed at a system level. Ideally, this happens at an actual deployment site, but we did face instances where we had to do part of our integration testing in our test environment to avoid any operational disruption while testing. For example, if you need to test a signaling system, you may need a test track, or you may have to reserve a track well in advance. So what we had was a representative environment that was good for functional testing, but not for security, because there was extensive use of simulators. So we did have a conversation around this earlier on during our design phase, now with our testing and commissioning engineers, and noted them as constraints for security testing, which allowed us some bandwidth to test the actual system before it entered the production space. And although this exercise was focused on the entire system, there was extra focus on the interfaces that crossed over subsystem and system boundaries. This included integration with security functions, say for monitoring or even remote access. And it was the same set of standards that we used for defining test plans. We're again used as guidance through this phase. 3-3 and the ISO Secures test specification for system security certification were used as guidance for our verification activities. And the system integrator took the lead on this phase, supported by our suppliers in fixing the issues. And in operational testing, the focus was to test the system in operational circumstances and validate if it meets the needs of the asset owner. And it was primarily around verifying the people and process elements, that is security roles, procedures within our organization, and how it would interact with the system for BAU. This was to really to verify if the gaps that we flagged during our design phase were all addressed. So we ran tests against the operations and maintenance scenario, that is around CSMS elements, say access provisioning, logical, physical access provisioning, monitoring, incident handling, and security's involvement in configuration change management to really assess if it works along with system specific roles, and also by the standards and procedures that were developed by our service providers. And 2-1 and 2-4, which discusses the asset owners and service providers security program requirements, were used as guidance through this phase. And it was the system integrator who worked along with the asset owners and suppliers to complete the operational testing. And post handover, it just became the owner's responsibility to continue security as a BAU. Now, just to wrap up, I wanted to highlight some key measures that helped us through this process. It was absolutely important to have project gates or the project assurance framework to explicitly define what artifacts are required across phases, because we ended up signing contracts with our subsystem service providers at different points in time. And we wanted all of them to align with the approach, regardless of when they signed and what their delivery timelines were, because there was a tendency to tweak the list of assurance artifacts for the late joiners to just to meet the timelines. And the 101 when it comes to handling projects, now defining clear roles and responsibilities across all phases for all entities. More importantly, to distinguish integrators and suppliers so that relevant requirements now derived from standards like 62443 are enforced. Although in some instances it was the same entity as the supplier and integrator. And system engineers, now we relied on their support heavily to define requirements, since they come with specific skill sets to ensure the requirements are concise, keeping it atomic so that it could be verified and validated. And we also had early contractor involvement arrangements that did help us in reducing the amount of misinterpretations on both the ends, the service providers and the asset owner, because we could workshop on the requirements and standards that the service providers need to adhere to and deliver on. And also we had independent assessors and reviewers across phases, just to establish an independent cybersecurity assurance case, like how the safety world has got independent safety assessors, primarily to review the outcomes of our risk assessments and system design, and also to perform validation during our integration testing phase, which really pointed us to some areas that we completely missed. So yeah, with that, I just want to thank you all again for listening, and over to you, Peter. Thank you.
Thanks, Kumar. And again, if you've got any questions for Kumar, please throw those into the Q&A. Again, I love kind of getting into some specific case studies and examples of how those standards are used across different industries and similar, and how the rail are same but different from like electricity and manufacturing, and especially kind of as you get into those type approvals and all the rigor that's required around that design. A question for you, kind of as you went through this process, and you kind of touched on it a little bit, but in terms of working with those third parties and suppliers and contractors and designers and things, what was your success in that, and getting them on board with the new philosophies and the use of 64.3 standards and similar?
Yeah, no, it was primarily to be flexible, Peter. So what we've understood is, yeah, we could define all the requirements that we want, but it is really up to service providers. If they don't have it, then yeah, they don't have it. So just have to be flexible around what our requirements are. So what we did was we did help our service providers on some instances where they didn't have enough maturity, because they've not been exposed to those requirements earlier. So it was a first time ask for them. So it was again a collaboration, a collaborative effort. Again, having those relationships, the right ones with our service providers to be flexible and to understand their point of view. When you have at least like 10 different service providers coming different maturity levels, and you want the same plans to be delivered and at same maturity, it's just not going to work. So you just have to be flexible with requirements and work along with them to benefit both the ends, to have a symbiotic relationship between both of us.
Yeah, for sure, and I think we've seen that as well, and great to see that you've experienced that kind of your success is the supplier's success and vice versa, and I think again, all organisations kind of benefit from that symbiotic, where you're educating your supply chain, especially kind of in these niche industries, especially in manufacturing and similar, where maybe there hasn't been a requirement and a drive previously around security, and again embedding security into the process, again coming back to Sarah's talk on that supply chain side, and I think that's kind of factored into kind of how and into your journey and rail in that same way. So thanks again, Kumar, for that talk.